I'm hoping optics, various work span topics in causal inference, machine learning, and computational genomics. He's an assistant professor at the Williams College, where he teaches courses on topics in causal reasoning, machine learning, and introductory computer science. Rohit's research is situated at the intersection of machine learning and statistics. He primarily works on developing principled methods for inferring causality from unstructured and messy data. He is also interested in the application and analysis of these methods in various contexts, such as computational genomics, cancer, immunotherapy, and algorithmic fairness. As a part of these efforts, Rohit also maintains an open source Python package for causal inference called analysts. So today we'll be talking about LLMs for proximal causal inference. So without delay, I'll hand it over to Rohit.
Awesome. Do I need to use the mic, or is it? Yeah, I'll put it on. Okay. Okay. Should I just turn it off?
Yeah, sure.
Yeah. Okay. Yeah, I'll project. I think it'll be okay. Yeah, thanks for having me here. Can everyone hear me like online and offline?
Yes, we can hear you online.
Okay, great. All right. So yeah, I'm going to be talking about using large language models for proximal causal inference. If you don't know what proximal causal inference is, I'll get into it. All right. So proximal causal inference with text data. This is a paper that I just wrote with one of my students, Jacob Chen. He was an undergraduate at Williams. So for context, Williams College only has undergraduate students. He's now doing his PhD at Johns Hopkins University with Ilya Spitzer. And this is joint work with a colleague of mine, Katie Keith, who's also at Williams College. Okay. So let me just situate this work in a broader context. So there's a few ways in which you can use causal inference in large language models in collaboration with each other. So one thing you can do is you can ask the extent to which large language models understand causation versus correlation. And there's nice work that's been done by folks at Microsoft Research, both in the US and India. And then there's another review paper that's written by Jin and Liu. And so this is just exploring, to what extent do we think that large language models can reason logically or causally. This is not what we're doing here. So I'll just go over things that we're not doing, and then I'll tell you what we are doing. So you can also use causal inference to improve LLMs. So you can try and use causal inference to deal with things like distribution shift, have them understand some sort of concepts, try and think of like what concepts they're actually using to generate their outputs. There's a slew of work in this area. And so here's a review paper if you're interested in that stuff. And then you can use causal inference, using some sort of supervised and semi-supervised natural language processing techniques for text data. So we're using text data in this paper, but I just want to note that there is a larger history of using supervised and semi-supervised machine learning methods with text. So these are some foundational papers that just ask the question, like, what does it mean for text to be a confounder? Or what does it mean for text to be a treatment in causal inference? That sort of stuff. And finally, this is what we're doing. So we're not in a supervised or semi-supervised setting. We are in a setting where we just have raw unstructured text, and we want to use large language models to generate what are known as zero-shot predictions. So the large language model hasn't been trained specifically for this task, but we ask it to read a bunch of notes and predict something about either a patient or a member of your population. And it could be really bad at that. It could be really good at that. And what we want to be able to do is encode some of that error and deal with some of the error that large language models are going to make when you ask them to do these complicated tasks without training them for it. So this is our Chen et al. There is another work that comes out of Microsoft Research in India, right here in Bangalore, actually. Okay, so that's what we're doing. We're going to be incorporating zero-shot prediction from LLMs for causal inference. Also, feel free to interrupt me with any questions just along the way. We can keep this nice and informal. Okay, so let's try and ground this in a concrete task. Yes. Yes. What is causal inference? So causal inference is you have a question. You want to know, let's say, you're a doctor or you're in the Food and Drug Administration. You're trying to approve medications. So causal inference is about like you have a causal question. You want to know whether one course of treatment versus another course of treatment is actually going to result in the patient getting better. Now, you could compute correlational quantities. You could just compute, among the people that received the treatment and among the people that didn't receive the treatment, who got better. But there's a number of reasons as to why people choose one treatment or the other. And those same reasons can also cause, better or worse outcomes. So there's always, correlation is not causation. We're always going to run into that issue. So one of the primary things we do in causal inference is separate association from causation. So the core of causal inference is how do you answer causal questions? Okay.
Hi, quick question from on.
Yes, yeah.
So I was wondering, so in tabular data sets, it's quite clear what the causal variables are. I was wondering whether it's quite clear in textual data what might be the causal variables.
Yeah, no, absolutely. So there is a large amount of literature that focuses on this question of what does it mean for text to be a treatment? So I'll give you a concrete example. So if you're analyzing social media posts and you want to know the effect of toxicity, like online toxicity on participation of male and female participants on an online forum, it's hard to define toxicity from text. The best you can do is sort of come up with some sort of indicators or markers of toxicity in text. And so there's a whole line of work about how do you summarize text into a treatment variable. When we think of treatment, especially and in causal inference, we often deal with binary treatments. Not always, but that's often the case. So it's like if you're dealing with a concept as complex as toxicity, how do you like binarize that as toxic versus non-toxic from text? That's not specifically what we're dealing with here. We're going to deal with text to infer some unmeasured confounding variable, and I'll go into like how you can make that a little bit more concrete.
Thank you.
Cool. Okay. So disclaimer, I'm not a clinician, but I do work with clinicians every now and then, especially during my time at Johns Hopkins, because we're affiliated with a hospital. So here's a grounding task, a causal question that you could ask. So let's say you're interested in developing a new medication for dealing with ischemic stroke. Here are the symptoms of stroke. You could have your face droop, you could have speech difficulties, arm weakness. Those are sort of the onset signs that you come across when you have a stroke. As a doctor, you're probably faced with this question. There's two courses of treatment you could pursue for somebody undergoing a stroke. You could give them a blood thinning medication, or you could give them a clot busting medication. And you want to know which one is better for the patient, right? So blood thinners, the way they act is they just make your blood thinner. And if your blood is thinner, that prevents clotting of the blood. But clot busters, on the other hand, they assume that the clots have already formed, and then they actively dissolve the clots. So they're two very different mechanisms. They're even administered in different ways. Blood thinners are typically given via oral medication, like capsules or tablets. Clot busters are typically injected, right? So you want to know which one of these treatment options leads to better outcomes, actually causes better outcomes. And there's a number of confounding variables over here. So for example, the severity of the stroke might affect which medication is given. The severity of the stroke can also affect what happens to the patient downstream. It could also be, things like their age, their sex, other underlying conditions can affect both treatment and outcome. So one of the classical ways in which we answer causal questions is to run a randomized trial where we remove the dependence on the confounders for treatment. So in a randomized control trial, you just flip a coin. If it lands heads, you give them one treatment. If it lands tails, you give them the other. And once you run that sort of trial, you can basically compute the averages in your treatment and control arms, compare those two, and you have a causal estimate. But many, many causal questions like this one, you probably can't run a randomized control trial for. So think about the urgency of a stroke. If you don't act on it quickly, the patient is going to suffer, long-term paralysis. And so you can't sort of have a patient come into the ER or the ICU and try and, talk to the patient and say, are you willing to enroll in a randomized experiment, right? A more extreme case would be if you want to determine whether vaping is bad for teenagers. A randomized control trial for that would involve flipping a coin and telling one teenager to smoke if it lands heads, and telling another teenager to not smoke if it lands tails, right? So clearly many randomized control trials are unethical and they just can't be run. Right? Okay, so this is our causal question of interest. Do we use blood thinners or do we use clot busters?
Quick
Cool.
question.
Yes.
Hi.
Yeah,
So I
question.
was wondering whether an RCT could be simulated even without access to randomization at experiment. So, for example, if some of the patients were given by the doctor's choice blood thinners versus, let's say, clotbusters, could those be sampled such that you're simulating a coin toss?
That's exactly what observational causal inference methods do. Sometimes they explicitly say that the goal of observational causal inference, so causal inference when you're using data that doesn't come from a randomized trial, is to simulate a randomized control trial. So what would the trial have looked like if you could have run it? Yeah. So that's
Right.
That's exactly what some of these methods do. Yeah. Good question. Okay. So we're interested in estimating what's known as the average causal effect. So this quantifies the mean difference in outcomes under two different interventions. So if I call my outcome Y and I call my treatment A, you might be curious why I don't call my treatment T. It's for historical reasons. In causal inference, A was known as the action variable. So what action do you take? So that's why it's A. Some people use X, but for historic reasons, I use A. Okay, so what are these quantities? So on the over here, I have the expectation of the outcome Y, given that I intervene, so I do, and give the patient A equals 1. So let's say we call that blood thinners. And I compare that with Y given do A equals 0. Note that this isn't a standard conditional expectation. So it's not the expected value of Y given A equals 1. And this isn't Y given A equals 0. So they're not just simple conditional expectations in general. If you ran an RCT, that's what it would be. But since we're not in an RCT scenario, we have to account for all these sources of spurious correlation, and that's why they're not equal to each other in general. Okay, so yeah, just a note again. So this do notation sort of comes from computer science, from UW Pearl. Again, so the do notation over here is saying we're going to intervene to give patients blood thinner, or we're going to intervene to give them this clot busting medication, right? So without assumptions, the average causal effect is not identified as a function of the observed data. So by non-identification, what we mean is that even if you have infinite data, you can't get an unbiased estimate of the quantity that you're interested in, or infinite data of the same kind. So it's about what quality of data you have, or what variables you've managed to measure. And the reason for that is because we never observe the same patient simultaneously under treatment and no treatment. So for any one individual, we only know what happened to them under do A equals 1 or do A equals 0. We don't observe both of their potential outcomes. So that's kind of the fundamental problem of causal inference, is that we don't observe both potential outcomes, and we need to deal with that somehow. So one of the classic ways of dealing with that, or the easiest assumption that we can make, is that there's no unmeasured confounding. Right? So what is a confounder? A confounder is any variable that affects both your treatment and your outcome. So this is a graph. It's a causal graph. What makes it causal? Well, you just add a causal interpretation to the edges. So an edge from A to Y here is indicating that A is a potential cause of Y. And then C to A and C to Y similarly means C is a potential cause of A and Y, right? So let's say we observe all relevant confounding variables C in our data. What might these be? So it could be age, sex, severity, family history. that determine treatment and outcome. If you do manage to observe all of that, then identification and estimation of the average causal effect is relatively straightforward. And here's how you would do it. So the expected value of y, given that you intervene and set a to some value little a, is given by what's known as the backdoor adjustment formula or the G formula. Right? So this formula has been reinvented a few times. It gets its name G formula from Jamie Robbins, who is an epidemiologist. And the backdoor adjustment formula comes from that name comes from computer science from UW Pearl. Okay, so what is the backdoor adjustment formula? You can think of it as a weighted average. So it's just the conditional expectation of the outcome, given that you receive a treatment and a set of confounders. So the value of your confounding variables, weighted by the probability of observing those confounding variables. Yeah. It could. It doesn't necessarily have to, but it could be the case that if a person is really old, maybe you're more tempted to give them clot busting medication than blood thinners, because maybe they're already on blood thinners, right? So something of that nature. Right. This is sort of a weighted average. It involves a marginal distribution over your covariates C and a conditional expectation of your outcome given A being equal to little a and C. And then you sort of average over this, right? So there's a summation involved. It turns out that really the only statistical modeling that you have to do is for this conditional expectation. So you can use your favorite regression method with some caveats. If you're going to use a machine learning method like neural nets, you have to make some smoothness assumptions and do a little bit more in terms of cross-validating or a version of cross-validating called sample splitting to make sure that you get good confidence intervals. How do you estimate P of C? It's just through the empirical distribution. So kind of like you just make a histogram of P of C. That's your empirical distribution, and that turns out to be good enough for that piece. So the relatively straightforward part is just as a caveat, this formula, for this equality to hold, this also requires that you have a positive distribution of treatment given your confounders. So it should be the case that there is positive support for both kinds of treatment given those confounders. Something known as consistency, meaning that when somebody receives the treatment, what outcome you observed is actually what would have happened. And then estimation can be tricky in high dimension. So that's the cursive dimensionality that crops up in just regular machine learning applications, right? But life is pretty good if you have no unmeasured confounders. But in reality, life isn't so good. You do have unmeasured confounders. So for example, I've added this variable u over here corresponding to an unmeasured variable. It could be that these other confounders cause it. It could be that u causes c. The c to u arrow is irrelevant. The most relevant part is that you have an unmeasured variable that causes a and y. And it's just not in your data, so you can't adjust for it. Right? You can't plug it into this backdoor adjustment formula. An example in the application we've been talking about is you could be thinking of atrial fibrillation, which is heart murmurs essentially. And often that a disease like that goes undiagnosed because the symptoms aren't obvious. And this could determine treatment and outcome as well. Okay. And so if you have this unmeasured variable, this G formula no longer works. It gives you biased estimates. Okay. All right.
And just to clarify what happens over multiple confounders, I guess you sum over all ancestors who are confounders. Is that the way to extend this?
Yeah, so C could be a set of variables. Yeah, and this summation would be over all of those variables.
I see. Okay, thank you.
Yeah. Okay. Cool. Okay. So there are a few responses people have had to this problem of unmeasured confounding. Here's one of them, which is fairly recent. It can be traced back to some works in 2014, but this exact formulation came out around 2020. So let's say you don't have access to U, but what you have access to instead is two proxies of U. Let's call them Z and W. and they're related to U and C in this way. In the exact setup of what's known as proximal causal inference, you can have a Z to A edge and a W to Y edge. But for simplicity, because I'm not going to need those edges, I'm just going to leave them out of this graph. Okay. So let's say you have these these proxies of the unmeasured confounders Z and W. They can't just be arbitrary proxies. They have to satisfy a few conditions. There's actually 4 conditions they have to satisfy. The first one is that they are independent sources of information about your unmeasured variable. So it should be the case that W is independent of Z given the unmeasured variable and your baseline covariance C. Okay. So you have 2 proxies. They should contain independent sources. They should be independent sources of information. The second is that one of the proxies, let's say W, should be independent of your treatment variable given U and C. Right? So one proxy should have nothing to do with your treatment, and the other proxy, let's say Z, should have nothing to do with your outcome Y. So Z should be independent of Y given A, U, and C. And then the last condition is a bit of the intuition behind it, what's known as completeness, is that W and Z should encode sufficient information about U. So it should be that the variability, there's sufficient variability in Z and W relative to U. Okay. It's easiest to explain in the discrete case. Well, one way to look at it is that the U to Z edge should be real. So it shouldn't be the case that Z is independent of U given C. And similarly, W should not be independent of U given C. So there should be some dependence between these 2 things. And the other condition that needs to hold, let's say if they're discrete, you can show that one way for completeness to hold is that if U is a binary variable, or let's say it's a discrete variable with 4 categories, then Z and W should also have at least 4 categories. So from an information theory perspective, it's just saying that Z and W shouldn't have less information than what's contained in U. Okay, so if all of these conditions hold, then identification is possible by a more complex functional than the G formula. It's called the proximal G formula, and it's given by this equation over here. So it's some function H of the treatment, the proxy W, and the covariance C times a probability of W and C. Okay, so what is H? H is a solution to this integral equation. It's not super important, but what is important to note is that a solution to this equation is guaranteed under the conditions P1 through P4. Okay. In practice, we don't actually solve an integral equation. There's an easier way to estimate this if you're willing to accept some smoothness conditions. An easier way to estimate this proximal G formula is to use a 2-stage regression. So you first run a regression of W as a function of Z, C, and A. W as a function of Z and C, and then you run a regression of Y as a function of W, Z, A, and C. The predicted versions of that. Okay. So that's the proximal G formula. It's really good if you have access to the kinds of proxies. The difficulty is, how do you find proxies that satisfy all of those conditions P1 through P4? Right. And our argument is that in general, it's quite hard to do unless you have a lot of domain knowledge about the problem. You might suggest, let's say, heart palpitations as one proxy, let's say Z. You might say shortness of breath is another proxy for W, and these are proxies of atrial fibrillation again. But there's no real reason to believe that heart palpitations aren't going to affect your outcome, and shortness of breath is not going to affect your treatment. Right? If you're short on breath, maybe you're not taking the oral medication, you're forced to take the injection, clot-busting medication. So this would violate the conditions P2 and P3 of proximal. Yes?
So I was wondering whether somehow you're trying to replicate a probabilistic map from W and Z to U. And then
That's exactly right.
yeah, okay.
Yeah. No, that's exactly right. What these proxies allow you to do is basically get especially in the if you're willing to accept that all of the variables C, Z, U, and W are discrete, you basically are able to invert some matrices that recover the probability of U given W. Okay, cool. So there's no reason to believe that these proxies are going to satisfy all of these conditions P1 through P4. So our goal is to construct Z and W in such a way that the proximal assumptions hold by design, right? So we're actually going to create these proxies ourselves and try and ensure that all of these conditions hold, P1 through P4. So here's our proposed solution. How do we ensure that these proxies satisfy proximal conditions P1 to P3? We're going to design these proxies using zero-shot predictions from text. So here's the actual way that large language models cropped up in our work was kind of coincidental. We were really studying the proximal G formula. And then we realized, well, if it's really hard for those conditions to hold, why don't we try and design them? And one of the ways that we thought about designing it is by using this unstructured data. So if it's hard to find proxies in your structured variables in like your tabular data, why not go to your text and have large language models look over your text and then predict these, give the large language model the clinician's notes and ask it, do you think this patient has atrial fibrillation, yes or no? Right. Now, the trick is still to say that there's no guarantee that these, if you do this arbitrarily, that the zero-shot predictions will satisfy the proximal conditions P1 to P3. And then, furthermore, you also want it to satisfy completeness. Right? So how do we do that? So here's just our working assumptions for our procedure. The first restriction that we have is we don't have any label data on you. So we wanted to make it really clear that, oh, yeah, question. Yes.
Tasks over text, which means that you're given like a lot of text classified to, let's say, 0.
No, so zero shot means that the model has been trained to do this task. So you have no label data. But yes, so you're given text. Let's say you're dealing with a medical application. So you're given text for each patient, and you're asking a model to predict a binary yes, no, or maybe a discrete classification thing task from that text. Okay, so the restriction is we don't have any label data on you. We wanted to make this really clear because in many applications, because of privacy concerns, maybe you can't have access to this data, and maybe you can't retroactively go and get this data if the patient's already been discharged from the hospital, let's say. Because if you do have some label data on you, you may as well use it. You would plug it into the backdoor adjustment formula. You might get high variance, if you have only a few patients where you've measured the unmeasured variable. But you can get variance reduction through other techniques, even by using patients on who you don't have that unmeasured data. So that's one restriction that we have. And then our two assumptions are as follows. The unmeasured variable that we're interested in can be expressed or encoded as a binary or discrete variable. It's not necessary. This assumption isn't necessary. But as many of you may know, zero-shot performance for regression is still quite poor. Right? So we leave it as a classification task. And then our second assumption, which is, again, not necessary, but really simplifies things and makes the theory more elegant, is that the text doesn't cause other variables. It's just a summary or record of events. Right? So it's clinicians or nurses or doctors writing down what happened. Yeah.
So in this sort of setting, how do I map it back to that causal graph? What is A and what is B?
Yeah. So let's say we look at this graph. The example that we're running with is that C is your set of baseline confounders. It could be things like age, sex, family history of disease. the disease that we're studying, let's say, is stroke. So we want to get a better treatment for ischemic stroke. And so A over here might be, do we give blood thinners or do we give clot busting medication? So A is our treatment variable. Y is our outcome, which could be, long-term paralysis or any adverse outcomes of stroke that you're trying to prevent.
My question is, how is do you want to extract that from text or?
We want to extract U, the unmeasured variable, which the example we're going with is atrial fibrillation. So C, A, and Y are measured, and we want to generate proxies of U, Z, and W using text. Yeah. Oh, nice. Any other questions? Awesome. All right. Okay, so those are our restrictions, those are our assumptions, and here's what the pipeline looks like. You start out with a set of notes for each patient. So you want to generate those proxies Z and W for each patient. So you start out with a bunch of notes for a patient. The first thing that you do is you filter this text to just text that involves stuff that happened before they receive the treatment. So you just keep the pre-treatment text around, right? What do you do then? You split the text into two pieces. This could be arbitrary, but ideally you don't do it in an arbitrary fashion. You try to generate independent instances of text. So we call that T-pre1 and T-pre2. For example, the patient has probably visited a lot of departments. So you could have notes from the radiology department and then notes from the echocardiogram technicians, for example. The nurse's notes versus the doctor's notes. And by independent, I'll make that more formal in a bit, but let me just give you a little bit of foreshadowing about that. By independent, we don't mean that these pieces of text are completely independent from each other. Clearly, they're about the same patient, so they're not going to be fully independent. What we mean is that they're just independent given the observed covariate C and the unmeasured variable U. Okay. So there's no additional stuff that we're missing that's in these notes. And then finally, you take these two pieces of notes. One of them you pass through a large language model and get zero-shot prediction. So let's say Google's FLAN T5. And then the other note you pass through a different zero-shot model. Let's say AI2 is Olmo, but could be ChatGPT, whatever your favorite large language model is. But the idea is that you use two different large language models. And I'll tell you why that's important in just a little bit. And then the final step is that we have a check. And essentially, the check is what's known as an odds ratio heuristic, which we use to just say, even if you followed all of this stuff, it could be that the proxies that you've generated don't satisfy those proximal conditions P1 through P4. So you want to have this check before you actually plug it into the proximal G form. And in graphical terms, here's what that entire process looks like. So you have your baseline confounders. They determine the text somehow. You have your unmeasured variable that also determines the other piece of text somehow. So these are your pre-treatment pieces of text. And then you're using these pre-treatment pieces of text to generate Z and W. And the reason I have them as dotted lines here is to indicate that these aren't real relationships that exist in the world, that we created these proxies through using these large language models, as opposed to just finding them in structured data. Cool. Any questions about that pipeline? Yeah. Yeah. Yes, they do. If T-pre1 and T-pre2 are independent given C and U, they will satisfy P1 through P4. Actually, let me backtrack on that. They will satisfy P1 to P3. They may still not satisfy completeness. And that's why we have this check. So the check is for, does it also satisfy P4? You ever follow up? Yeah, so P4 is completeness. Let me just go back to the the proximal conditions. Okay, so P1 is that the proxies should be independent of each other given U and C. If you have text that's independent given U and C, then this condition gets satisfied, right? Same with P2 and P3, right? Our heuristic still checks whether you have residual confounding that's not through C or U, which might violate P1 to P3, but we have a check for that. And then finally, the last one is that Z and W should be predictive of U. That's the completeness condition. And that one, we still have to check because it could be that your large language model's predictions are just arbitrarily bad, right? So your large language model essentially randomly guessed. So you want to still ensure that Z and W are indicative of something about U. Yeah. Yeah. Yes.
I feel like there would be two ways to do it, right? Like, so I think what you are saying is you're deriving W and Z from the language model.
Yeah.
But and I'm guessing there's some sort of numerical yes no based on T31 and T32. I was wondering whether there could be an encoding of T1 pre and T2 pre, and that could be used for as the conditionals.
You mean like embed T pre1 into some space and yeah, no, of course. So we're using large language models here. Again, like large language models are coincidental to this work. You can use any zero-shot model you want, which could involve embedding T pre1 into a space, embedding T pre2 into a different.
In this case, you're deriving from T1 pre and T2 pre W and Z, which are 0, 1 variables, and then
Exactly. Yep. Good questions. Thank you. Yes. Are we assuming that T2 pre has no effect on A? Yeah, so that comes from one of our assumptions where we say that the text is a record of events as opposed to actionable items. Absolutely. And it turns out that, in fact, if one of these affects the treatment, it's fine. And if one of them affects the outcome, that's fine. But we sort of keep it simple as like they're a record of events. And there are plenty of, you're right, there is plenty of text that could be actionable, but there are plenty of things that are just sort of like, here are the procedures that we did to this patient. Like the patient arrived, this is what happened, and then there's no like follow-up that's done. Yeah, that's a great question. Cool. Okay. So that's the pipeline. So let me try and justify each of the steps in this pipeline. So it's like a little bit involved. Let me tell you why this is sort of revisiting a history of how we sort of stumbled through a few different iterations of this algorithm and arrived at this. So let's walk through the intuition. So all the proofs are in the paper. They're actually really simple. They're very just based purely off of graphical conditions. But I'll give you the intuition here. Okay, so the first one is and this actually came out of my student who was working on this paper. He had read a few articles where people were directly using zero-shot predictions from large language models in the G formula, the backdoor formula. So suppose we try to avoid the complications of proximal causal inference, and we just use predictions of one of our zero-shot models, so let's say W, as a direct substitute for the unmeasured confounder in the backdoor formula. So in general, W is not going to be equal to U. Your large language model is not going to have 100% accuracy. It's going to be an open path through U, and we still get bias. So this isn't like a very deep statement. It's just a statement that we felt we needed to make because here's what the G formula would look like if you had U. Here's what the G formula looks like if you just have W. And it's pretty clear that these two equations are not going to be the same, or these two formulae are not going to be the same in general. There are exceptional conditions under which they might be. If the weighted averages sort of, they average out to be the same, but unlikely to hold in practice. Okay, so here's a more interesting proposal. Why do we say that you should filter out the post-treatment? Why are we only using pre-treatment text? So here's the proposition. we came up. W and Z are both inferred using zero-shot models on that has any post-treatment, then we show that the resulting proxies are going to violate either P2, P3, or both. Right? So here's what that would look like. So here's some text. Maybe you grab some text that comes from when after the patient was discharged. So you have causing the treatment, the text. And then you try and infer Z and W text, right? So if you recall, we want that one of the proxies is independent of Y given A, U, and C. So Z should be independent of given A, U, and C. But you have this path Y, T that sort of violates that independence. Similarly, you can show that in this case, P2 doesn't hold either because you wanted that W was independent of A given U and C, but you have the A to Y to T to W. Okay, so if you generate proxies in this way, it leads to bias in the proximal G formula. Now, a note here is that if you know some stuff about causal inference, it's well known that even for the backdoor adjustment formula, you should never adjust for covariates that are post-treatment. And that never there is strong. It turns out under special conditions, you can use post-treatment information to say something about the causal effect. But this is, an analogous result for the proximal G formula about why you shouldn't use post-treatment information. And similarly, in the appendices, we point out if you can use post-treatment text, but to make your life and the pipeline simple, you should avoid using it. Okay. All right. So why do we split the text? So let's say if W and Z are inferred via zero models on the same instance of pretreatment text, so we don't splitting, that clearly violates P1, right? So we want the proxies to be independent of each other given C and U, but if you don't split the text, you just have a pre-W path, and so you're no longer okay for the condition P1. Yes.
Sorry, this is my basic question. For the entire pipeline, the language model comes in to get you W and Z.
Yes.
But apart from that, everything else is on the causal inference pipeline. No language.
Exactly. Yeah, exactly. So those are really just for these two edges, and everything else is causal inference. Yeah. Okay. That's the second thing to avoid. So that justifies why we should split the text. And finally, why do we use two zero-shot models? Why can't we use just one? So this is what it would look like if we used one. I've just used the same color purple over here for both these edges to indicate we're using one model, and then two colors here to indicate wheels. So once we split the text, are we okay to use a single zero model, or is it still necessary to use different ones? So it turns out, theoretically, you're okay doing this. But empirically, we found that you should be doing this. What's the reason for that? Some intuition is just that use the same zero-shot model. It's likely to make the same predictions, regardless of the text that you get, or the same errors. And so in practice, you won't have the proxies being independent of each other, despite having split the text. Okay, but here's a theorem, which just says that if W and Z are inferred using zero-shot classification, whether you use one model or two models, then P1 to P3 holds. And additionally, if W and Z are predictive of U at all, so even weakly predictive of U, then P4 holds. So here's a sketch of that proof. Conditions P1 to P3 are just confirmed using this criterion known as D-separation in the causal DAGs. So what D-separation just allows you to do is, determine conditional independencies given a graph. So these conditions are verified just using D-separation. For P4, if Z and W are even weakly predictive of U, then a sufficient condition for completeness is this. So basically, it's what I mentioned earlier. If U has, say, 4 categories, Z and W should also have at least 4 categories. And if that's true, you're good to go. And this is true by assumption of the zero-shot prediction task, and by assumption about U, that U can be encoded as some discrete variable. Yes.
W and Z are not one variables for.
Exactly. Yes. Yeah. So this theorem holds even if W and Z are not even if U, W, and Z are not binary.
In that case, like one extension of the could perhaps be if W and Z are directly things of T1 tree and T2 tree, and that might encode a lot of data, but then completeness might be an issue.
Yeah. So if W and Z are high dimensional, that makes inference tricky. Because at some point to do inference where you fit a regression for W as a function of Z. And so that would be a potential review and Z.
And typically, what is the size of the data sets you're
looking? Do you mean like in terms of number of rows? It depends entirely on the application. In the specific application that we were dealing with, which is electronic health record data, we had about 8,000 rows of data. Yeah. So it's not super high, not super big data settings. It could be high dimensional in terms of number of variables, but not in terms of number of rows. Great. Any other questions about that? Okay. All right. Okay. So using zero-shot model. Oh, yeah. Is that a question?
Hi, does the split affect which W and C we find?
Oh, that's a good question. So it turns out it's symmetrical here. So it doesn't really affect which one is inferred using which zero-shot model. It would matter if you decide to use some post-treatment text.
So we can get multiple pairs of W and C depending by varying which which condition we are splitting the text on, right? Could
Absolutely, yeah. So you could generate and in fact we sort of do this. We use a variety of zero-shot models. We use a variety of splits of text. Combining all of those is tricky. A separate paper I've written that's not explicitly about combining these proxies, but it's about given any k set of causal models, how do you design a causal like a null hypothesis test of is there a treatment effect, yes or no? If you have like k causal models, and some of them could be wrong and incorrectly specified, but at least one is correct.
Okay,
and we
so
have a way of giving you the right answer.
Rank them or pick the more discriminating one.
Yeah, so ranking. When I get into the odds ratio heuristic, I'll come back to that question of ranking. It's not actually super obvious. Like you'll notice that all of the conditions P1 to P3 and P4 involve something about the unmeasured variable U. So all of the assumptions of proximal causal inference and by extension, the stuff that we're doing here, these assumptions are untestable because they have a dependence on U. And so coming with a way of ranking it is a little tricky, actually. We have a falsification heuristic, but that's not the same as verification. So by testability, you could mean two things. One is, can you falsify the model when the assumptions do not hold? And the other is, can you verify the assumptions when they do hold? So it turns out we have a way of falsifying, but we don't have a way of verifying. So that it sort of protects you from getting the incorrect answer, but it could lead to certain occasions where the assumptions were okay, but you still rejected the proxies.
Okay, thanks.
Cool. All right. All right. So empiricism. What is empiricism? What do we see empirically? So using two distinct zero-shot models is better in practice. And again, the intuition is just you might violate P1 in practice if you use the same zero-shot model. Okay. All right. So the odds ratio heuristic. What's the check that we have over here? So despite following that step-by-step process, it is still possible that the proxies don't satisfy P1 through P4. And that could happen for a number of reasons. It could be that the text that you have is just uninformative for the unmeasured confounder. It could be that the one or both of your zero-shot models just generate predictions that are basically random, so they're not actually very good at the task that you gave them. Or it could be that the proxies are not independent from each other due to some information leakage in the text, or between the zero-shot models, right? And this leakage, this information leakage is something that you can't attribute to just C and U. Right? So again, these modes of failure are untestable in general. So what we do is we propose a way of falsifying it, not verifying, but at least falsifying to flag when to stop. And the reason we're okay with that is usually in causal inference, we try to be fairly conservative about it. Making a causal claim is a big deal. It's supposed to inform treatment decisions. Sure, it's better to stop than to proceed in most settings. Okay, so checking the odds, using the odds ratio heuristic, here's how it works. So the conditional odds ratio function is defined as follows. Many of you might have seen the definition for just binary variables, but this is the general definition of the conditional odds ratio function. So it's a ratio of two odds, as its name indicates. So the first odds is the probability that W takes on some value, as opposed to some arbitrarily chosen reference value. Let's say it's so the probability that W takes on some value as opposed to 0, given that Z is equal to some value and X. So this is the odds ratio of W and Z given X. So that's one odds. The other odds is the odds that W takes on some value as opposed to its reference when Z is at its reference value. Okay. What makes the odds ratio nice is that it's a non-parametric measure of association. It ranges, some number between 0 and infinity. If it's below 1, that indicates negative association between W and Z given X. If it's above 1, they're positively associated given X. And if it's exactly 1, so if the odds ratio is 1 for all values of W, Z, and X, this is if and only if W is independent of Z given X. Do you have a question? Okay. So here we treat W and Z as a single free parameter that's estimated under a parametric or semi-parametric model. This is a pretty common assumption or a pretty common strategy for estimating the conditional odds ratio is you just assume a semi-parametric model and run with that. Okay, so how does the odds ratio help us? So if all goes well, the proxies are independent given U and C. And so the conditional odds ratio of W and Z given U and C should be equal to 1. Yes.
So I think that understanding is right.
Yes.
In this case,
That's
something close.
That's right. Yeah.
And
And you can use, you can construct a test statistic. You can get p-values. You could make confidence intervals. Yes. Yeah. There is a reason we pick the odds ratio. It does show up in estimation sometimes. The other thing is that its values have a nice interpretation, and we use like bounds on the values to decide. So if you use an arbitrary independence test, you should make sure that the value that you get out of it has some interpretation.
So you're using gamma in your theorems.
Yes. Yeah. Yeah, but that's a really nice question. Yeah. So any independence test works, but in practice we use the odds ratio. Okay, so if all goes well, then the conditional odds ratio of W and Z given U and C is equal to 1. Again, this isn't a thing we can compute because we don't have access to U. So what we do is we set bounds instead on the observed odds ratio, W and Z given just C, right? And what we show is that this is a reasonable bound for that odds ratio if all is gone. The lower bound is 1. Why is the lower bound 1? If W and Z are predictive of U, this is a reasonable lower bound, because if it's equal to 1, that means they're just completely independent of each other. So that must mean that you don't have this path U to Z and U to W. And so you just get independence between those two. If it's below 1, that means that one of these were anti-correlated or negatively associated with the with U. That also is a weird thing for your large language model to be doing. And then we show that an upper bound is just some check that the correlation between W and Z is attributable to just U. So we're conditioning on C. So the only path we're leaving open is Z through the text to U and then down to W. So there's just this one open pathway. So it should be the case that the correlation between Z and W is not 1, but it's also not super high. It should have some bound. Now, what is that bound? Unfortunately, that's user specified and domain specific. We set a generous upper bound of 2. And so, depending on how you set this bound, you may end up rejecting more or more models or more proxies or fewer proxies. But this generous upper bound of 2 is sort of just saying that, the odds that W is 1 when Z is 0 versus 1 is at most 2. Right? So that's a pretty high upper bound. Okay. So how does this work in practice? So here's the results for the fully synthetic data. P1M just means we used one zero-shot model for proximal causal inference. Same means that we didn't split the text. And then P2M is 2 zero-shot models. And then P2M same as 2 zero-shot models, but we didn't split the text. So here's what happens. Remember that we said that splitting the text was important. So if you don't split the text, whether you use one zero-shot model or not, when you compute the odds ratio between W and Z given C, you can see that they're way above any generous upper bound that we set. So when you use the same piece of text and the same zero-shot model, it's basically infinity because the predictions are essentially the same. If you use 2 zero, really, really high, right? If you're using the same instance of text. So this is our fully synthetic experiment. So the fully synthetic experiments agrees with our theory that using one zero-shot model in theory is okay. So if you look at this odds ratio, it's pretty squarely below that upper bound. This odds ratio is also reasonably within that upper bound and above 1. And then you can see the bias in our causal effect estimates. This is super small, this is super small, and these are way higher, right? So just to summarize that, the fully synthetic results show that splitting text is necessary, and then one zero-shot model is sufficient in theory. Here's what happens in practice. So what we do is we take this data from Mimic3, which is an electronic health record database. We have real clinical notes from Mimic3. We have real covariates and unmeasured variables. So we take turns in hiding one of the variables from our proximal causal inference pipeline. And then we treat several, so that basically we treat several different covariates as U in our experiments. And because we're doing causal inference, we have no access to ground truth in general. So we have a synthetic treatment A and outcome Y. Right? So unlike machine learning, you don't have ground truth for causal inference. And so often the best you can do is semi-synthetic. And if you have questions about how to get even more realistic evaluations, I'm happy to discuss that offline. Okay, so here are the results of the semi-synthetic experiments. So we infer one of the proxies using echocardiogram notes, the other one from radiology. And here we're using echo and dosing. And in this case, our unmeasured variable is atherosclerosis, something related to atrial fibrillation. This is congestive heart failure. And then this is what happens with one model versus two models. So this is the idealized scenario. If we were able to actually compute the odds ratio given U and C, this is what we actually get access to, the odds ratio given just C. So you'll notice that when we use just one zero-shot model, none of the proxies pass that odds ratio heuristic. When we use two of them pass, one of them doesn't. This one just barely doesn't pass. Right? So this is kind of again underlying the importance of using two zero-shot models in practice, and that the odds ratio heuristic protects against bad proxies. So let me justify the fact that when these are red, we are indeed getting biased results. So if you look at these, here's the true average causal effect. This is kind of this was just to beat up on what happens if you use the backdoor adjustment formula directly with the proxy. You just plug in the proxy without using proximal inference. So this is clearly biased in all cases. When the odds ratio heuristic doesn't pass, which is highlighted in red, using one zero-shot model, we get bias. So these confidence intervals kind of cover the truth, but they're not centered, right? They're not centered at the truth. Here we get really good coverage. Here this is clearly biased with one zero-shot model, but we get good coverage here. And this is an example of maybe a false flag, right? Where the proxies could have been used, our odds ratio heuristic rejected it, but it's in our minds it's again better to be safe or more on the conservative side. And this is, again, a parameter that the analyst can play around with if they're interested. Okay, so you can use this approach with other kinds of text. For example, political speeches, multiple speeches of the same candidate. You could use it using Reddit posts, again, multiple posts of the same person, or multiple Twitter posts of the same person. So just pointing out that this isn't exclusively related to the medical field. And then here's some ideas for future work. So applications with different kinds of text data. Better and data-driven ways of determining that upper bound on the odds ratio. So one thing that people often do in the field of sensitivity analysis is that you try and determine the biggest correlation you could see in your data set. So you compute a bunch of pairwise correlations and you set that as your upper bound. That leads to a few problems in inference downstream because you're doing a bunch of tests, essentially. So there's stuff to resolve over there. Robustness to failures in zero-shot predictions, maybe like combining proxies, some of which are good, some of which are bad. And how do you get robustness to some of the bad predictions? And then finally, better nonlinear estimators. So that two-stage regression, we use parametric models. It is possible to use kernel regression under certain smoothness assumptions, but again, that comes with at the cost of other things that you need to do with your data. You need to set up a cross-validation scheme to get the principled confidence intervals. All right, and that is all I have for today. Thank you. And I'm happy to take more questions either here or offline. Yeah.
Actually, I was wondering whether closeness to AC would be a better metric than odds ratio. So, why are you distinguishing the three, or maybe I didn't understand why you are distinguishing the three methods based on how good they are on odds, how low.
Yeah. Okay. So the only reason we have this ground truth is because this is semi-synthetic data. In reality, you don't have access to this ground truth. This is what you're trying to estimate. So this green line that you see here is just, it's not available to the analyst when they're actually running this method.
So this is the only graph that matters, right? Not the other one on odds ratio.
This is the only graph that matters downstream, but this is the only thing the analyst has access to determine whether their method is going to do okay when they actually estimate the causal effect. Yeah, that's a good question. Any other questions? Cool. All right. Thank you. Yeah, there's additional stuff in the paper. And there's also code if you're interested. Oh, thank you. Thanks.